far beyond the orbit of Neptune, where the Sun appears as nothing more than a distant star. A frozen world drifts through the darkness of deep space. It is covered in bright reflective ice, locked in temperatures colder than almost anywhere in the solar system, and it takes more than 550 years to complete a single orbit around the Sun. This distant world is called Eris. When astronomers first discovered it in 2005, it immediately created a problem. Eris appeared to be about the same size as Pluto, possibly even larger, and if Pluto was considered a planet, then Eris should be one too. But that raised an even bigger question. If Eris was a planet, how many other planets might still be hiding in the outer solar system? The discovery sparked one of the most controversial debates in modern astronomy, a debate that would eventually change how we define planets forever, because Eris didn't just reveal a new world, it changed the solar system itself. Far beyond the familiar planets of the inner solar system lies a vast and mysterious region filled with frozen remnants from the earliest days of planetary formation. This distant realm stretches far past the orbit of Neptune and contains countless icy bodies drifting through the cold darkness. For most of human history, this region was completely unknown. Even powerful telescopes could not easily reveal what existed so far from the Sun. But over the last few decades, astronomers have slowly begun to uncover a hidden population of distant worlds. Among them is one object that would ultimately change how we define planets themselves: Eris. To understand why Eris became so important, we first need to explore the strange region of space where it lives. This area is known as the Kuiper Belt, a vast ring of icy objects orbiting the Sun beyond Neptune. It begins roughly 30 astronomical units from the Sun, about 30 times the distance between Earth and our star, and extends outward for tens of billions of kilometers. The Kuiper Belt is often described as a frozen archive of the early solar system. The objects there formed over 4 billion years ago, at the same time as the planets, but many of them never merged into large worlds. Instead, they remained small and icy, preserving clues about how the solar system originally formed. For centuries, astronomers believed that Pluto was the lone planet occupying this distant region. When Pluto was discovered in 1930 by Clyde Tombaugh, it seemed to be the mysterious Planet X that astronomers had been searching for. It was small, faint, and extremely distant, but it fit the description of a ninth planet orbiting beyond Neptune. For decades, Pluto remained alone in the outer darkness, but as telescopes improved and digital imaging technology advanced, astronomers began discovering other objects beyond Neptune. At first, these objects were tiny, only a few tens or hundreds of kilometers across. They were interesting scientifically, but none of them threatened Pluto's position as a planet. Then, in the early 1990s, something unexpected happened. Astronomers confirmed the existence of the Kuiper Belt itself. In 1992, two scientists named David Jewitt and Jane Liu discovered the first confirmed Kuiper Belt object after Pluto and its moon Charon. The object was small, but it proved something revolutionary. Pluto was not alone. It was simply the largest member of a vast population of icy bodies. Over the following years, dozens of new Kuiper Belt objects were discovered, then hundreds, eventually thousands. Each new discovery slowly reshaped our understanding of the outer solar system. Instead of being a lonely planet, Pluto now appeared to be part of a much larger family of distant icy worlds. Astronomers began asking an important question. If Pluto was just one object among many similar bodies, should it still be considered a planet? At first, the answer seemed simple. Pluto was still much larger than most of the newly discovered objects. Even though the Kuiper Belt was full of icy debris, none of those objects came close to Pluto's size. But that assumption would soon change. Throughout the late 1990s and early 2000s, telescopes became more powerful. and surveys of the outer solar system became more systematic. Astronomers began scanning large areas of the sky with digital cameras, capable of detecting extremely faint objects moving slowly against the background stars. Among the scientists leading this search was an astronomer named Mike Brown at the California Institute of Technology. Brown and his team were determined to explore the outer solar system more thoroughly than ever before. They used powerful telescopes equipped with wide-field cameras that could capture enormous regions of the sky in a single exposure. The goal was simple: find new worlds. But what they eventually discovered would create one of the biggest controversies in modern astronomy. By the early 2000s, Brown's team had already discovered several large objects in the Kuiper Belt. Some were surprisingly big, almost as large as Pluto itself. One object named Quaoar measured over 1,000 kilometers across. Another object called Sedna followed an extremely distant and unusual orbit that extended far beyond the Kuiper Belt. These discoveries suggested that the outer solar system might contain many large objects still waiting to be found, but none of them were quite large enough to challenge Pluto directly. Then, in January 2005, Brown's team made a discovery that would shake the entire astronomical community. Using the Samuel Oschin telescope at Palomar Observatory in California, the team identified a faint moving object in the constellation Cetus. At first, it appeared to be just another distant Kuiper Belt object, but as astronomers measured its orbit and brightness more carefully, they realized something extraordinary. This object was incredibly far away, nearly 96 astronomical units from the Sun at the time of discovery. That meant it was almost 3 times farther from the Sun than Neptune. Even more astonishing was its size. Based on the amount of sunlight it reflected, the object appeared to be roughly the same size as Pluto, possibly even larger. If that estimate was correct, then astronomers had just discovered a 10th planet. The object was originally given the temporary designation 2003 UB313 because the images used to identify it had actually been taken 2 years earlier in 2003. Like many discoveries in astronomy, it took time for scientists to analyze the data and confirm what they had found. But once the discovery became public, it spread rapidly across the world. Headlines appeared everywhere, announcing that a new planet might have been found beyond Pluto. The discovery sparked excitement among the public and intense debate among scientists. If 2003 UB313 truly was larger than Pluto, then it seemed logical to classify it as a planet. But that immediately created a new problem, because if one object beyond Pluto was large enough to be called a planet, then there might be many more similar objects still waiting to be discovered. In fact, some astronomers suspected that the Kuiper Belt could contain dozens of Pluto-sized worlds. If every one of them were considered a planet, the solar system might suddenly contain dozens of planets instead of 9. This possibility forced astronomers to confront a difficult question. What exactly defines a planet? For centuries, the word planet had been used somewhat loosely. Historically, it simply referred to objects that moved across the sky relative to the background stars. Ancient astronomers used the term to describe Mercury, Venus, Mars, Jupiter, and Saturn, the 5 planets visible to the naked eye. Later discoveries added Uranus and Neptune to the list. Pluto became the 9th planet in 1930, but no strict scientific definition of the word planet had ever been established. Now, the discovery of 2003 UB313 made that ambiguity impossible to ignore. If astronomers continued calling Pluto a planet, they would likely have to add many more objects to the list. But if they wanted to avoid a rapidly growing number of planets, they might need to redefine what a planet actually is. The debate quickly intensified. Some astronomers argued that Pluto should remain a planet because of its historical significance. Others argued that the classification should be based on physical properties rather than tradition. Meanwhile, scientists continued studying the newly discovered object in more detail. They measured its orbit and discovered that it followed a highly elliptical path around the Sun. At its closest point, it approached about 38 astronomical units from the Sun, slightly closer than Pluto's orbit. But at its farthest point, it traveled more than 97 astronomical units away. This extremely stretched orbit meant that the object spent most of its time in the deep outer solar system, far beyond the Kuiper Belt. Astronomers also noticed something else unusual. The orbit of 2003 UB313 was tilted significantly relative to the plane of the solar system. Most planets orbit within a relatively flat disk around the Sun, but this object's orbit was inclined by about 44 degrees. That made it one of the most tilted large objects known in the solar system. As scientists gathered more data, they realized that this distant world was not only large, but also incredibly reflective. Its surface reflected almost all the sunlight that reached it, making it one of the brightest objects in the outer solar system. Eventually, astronomers concluded that the object's surface was likely covered in frozen methane ice, which reflects sunlight extremely efficiently. This bright, icy surface helped explain why the object appeared so large in early measurements. Nevertheless, the discovery remained astonishing. Here was a distant world, comparable in size to Pluto, orbiting the Sun in the far outer darkness, and its discovery forced humanity to reconsider something that had seemed unquestionable for generations. Was Pluto really a planet, or was it simply the first known member of a much larger population of distant icy worlds? The newly discovered object would soon receive a permanent name, one that perfectly captured the chaos its discovery had unleashed. It was named Eris, after the Greek goddess of discord and conflict, a fitting name for the world that would ignite one of the greatest debates in the history of planetary science. As astronomers continued studying the newly discovered object, known as 2003 UB313, it quickly became clear that this distant world was unlike anything scientists had seen before. Not only was it extremely far from the Sun, but its orbit suggested that it belonged to a very unusual class of objects in the outer solar system. To understand why Eris was so extraordinary, we first need to look at the chaotic architecture of the distant solar system. Beyond Neptune, space is not empty. Instead, it is filled with thousands of icy bodies left over from the formation of the planets. These objects are remnants from the early solar system, fragments of material that never combined to form larger planets. Over billions of years, the gravitational influence of the giant planets, especially Neptune, scattered many of these objects into strange and unpredictable orbits. Some remained within the Kuiper Belt, orbiting the Sun in relatively stable paths. Others were pushed much farther away, entering a region known as the scattered disk. The scattered disk is a distant and chaotic region populated by icy worlds with highly elongated and tilted orbits. These objects are constantly influenced by the gravitational pull of Neptune, which can slowly alter their trajectories over millions of years. When astronomers calculated the orbit of 2003 UB313, they realized it did not behave like a typical Kuiper Belt object. Instead, it belonged to this scattered disk population. This meant the object's orbit was both stretched and steeply inclined relative to the flat plane of the solar system. At its closest approach to the Sun, known as perihelion, the object came within about 38 astronomical units, similar to Pluto's distance. But at its farthest point, aphelion, it traveled nearly 100 astronomical units away. At that distance, sunlight becomes incredibly faint. The Sun would appear only slightly brighter than a star seen from Earth. Temperatures on the surface would fall to around -240 degrees Celsius, cold enough to freeze gases like nitrogen and methane into solid ice. Despite these extreme conditions, Eris reflected sunlight extremely efficiently. Astronomers measured its brightness and realized that its surface must be one of the most reflective in the solar system. The reason likely lies in its chemistry. Eris is believed to be covered in methane ice similar to Pluto, but because Eris spends most of its orbit extremely far from the Sun, these frozen gases remain stable on its surface. Methane ice reflects sunlight almost like fresh snow, giving the dwarf planet an unusually bright appearance. As astronomers analyzed the data more carefully, they also began searching for moons orbiting this distant world. Finding a moon around a distant object is extremely valuable for scientists because it allows them to calculate the object's mass. By measuring how long it takes a moon to orbit its parent body, astronomers can determine the strength of the gravitational pull between them. In September 2005, scientists made another remarkable discovery. Using the Keck Observatory in Hawaii, one of the most powerful telescope systems in the world, astronomers detected a small moon orbiting 2003 UB313. This moon was later named Dysnomia. Dysnomia is relatively small compared to Eris, measuring only about 700 kilometers across, but its discovery provided a crucial piece of information. By observing Dysnomia's orbit, scientists could finally calculate the mass of Eris itself. The results were astonishing. Eris turned out to be about 27% more massive than Pluto. This meant that even if Pluto and Eris were similar in size, Eris actually contained more total material. It was slightly heavier and therefore slightly more gravitationally dominant. In other words, Eris was not only comparable to Pluto, it might actually be the largest known dwarf planet in the solar system. This discovery intensified the debate within the astronomical community. If Pluto was considered a planet, then Eris should logically be one too. After all, Eris was at least as large and even more massive. But if Eris was a planet, what about the other large objects astronomers were starting to discover? Around the same time, scientists had identified several other distant worlds approaching Pluto's size. Objects such as Haumea and Makemake were also large enough to raise questions about their classification. Suddenly, the solar system appeared far more crowded than anyone had imagined. If Pluto remained a planet, the list of planets might soon grow rapidly. Some astronomers predicted that within a few decades, the solar system could contain 20, 30, or even 50 planets as new discoveries continued. For many scientists, this outcome seemed impractical. The term planet had always implied a relatively small group of dominant worlds orbiting the Sun. Expanding that list indefinitely would blur the distinction between planets and the countless smaller objects scattered throughout the solar system. But deciding how to draw that line was not easy. The debate reached its peak in 2006 when the International Astronomical Union (IAU), the organization responsible for officially naming and classifying celestial bodies, gathered for its General Assembly in Prague. One of the main topics on the agenda was the definition of the word planet. For the first time in history, astronomers would attempt to create a formal scientific definition. Several proposals were considered. One early proposal suggested that any object large enough to become spherical under its own gravity should be classified as a planet. According to this definition, Pluto would remain a planet, and Eris would join the list as the 10th planet. However, this definition would also include several other large objects, increasing the number of planets significantly. Another proposal suggested a stricter requirement. A planet must not only orbit the Sun and be spherical, but it must also clear its orbital neighborhood of other objects. In other words, a true planet must dominate its orbit gravitationally. This meant that over billions of years, the object would either absorb or scatter most other material near its path around the Sun. Under this definition, the 8 major planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, clearly qualified, but Pluto did not. Pluto shares its orbital region with countless other objects in the Kuiper Belt, and Eris did as well. After days of discussion and debate, the International Astronomical Union voted on the new definition. The final decision established 3 criteria for a planet. First, the object must orbit the Sun. Second, it must have enough mass for gravity to shape it into a roughly spherical form. Third, it must have cleared the neighborhood around its orbit. Pluto satisfied the first 2 conditions but failed the third. and so did Eris. As a result, both Pluto and Eris were placed into a new category of celestial objects called dwarf planets. This decision officially reduced the number of planets in the solar system from 9 to 8. The announcement sparked enormous public reaction. For many people around the world, Pluto had been considered a planet for their entire lives. Textbooks, classroom models, and popular culture all recognized Pluto as the 9th planet. Now, suddenly, that classification had changed. Some people accepted the decision as a natural result of scientific progress. Others strongly disagreed, arguing that Pluto's historical status should be preserved. But regardless of public opinion, the new definition became the official standard used by astronomers. Ironically, the object that triggered the entire debate, Eris, also failed to qualify as a planet under the new rules. Instead, it joined Pluto as one of the most prominent members of the newly created dwarf planet category. In a sense, Eris had accomplished something extraordinary without ever being visited by a spacecraft and without even being widely known by the public. This distant frozen world had forced humanity to rethink the structure of our own solar system. It had rewritten the definition of a planet itself. And yet, despite the controversy surrounding its discovery, Eris remained one of the least explored worlds in the solar system. No spacecraft has ever traveled there. No probe has ever photographed its surface up close. Everything scientists know about Eris comes from telescopes observing a faint point of light billions of kilometers away. But even from that distance, Eris continues to reshape our understanding of the outer solar system because its discovery reveals something profound. The solar system is far larger, more complex, and more mysterious than we once believed, and Eris may be only one of many hidden worlds still waiting to be discovered in the darkness beyond Neptune. Even after the intense debate over Pluto's planetary status settled, Eris continued to fascinate astronomers for another reason. Unlike Pluto, which had already been explored by the New Horizons spacecraft, Eris remained an extremely distant and mysterious world. Everything scientists knew about it came from faint points of light captured by telescopes millions of times farther away than the distance between Earth and the Moon. Studying such a distant object is incredibly challenging. Eris lies billions of kilometers from Earth, and even the most powerful telescopes can only detect tiny changes in brightness and color. But astronomers have developed clever techniques that allow them to extract remarkable amounts of information from those faint signals. One of the first questions scientists wanted to answer was simple. What does Eris actually look like? Because Eris is so far away, telescopes cannot easily resolve its surface into visible features. Instead, astronomers analyze the light reflected from the object by spreading that light into a spectrum, separating it into its different wavelengths. Scientists can identify specific chemical signatures on the surface. When researchers performed these observations on Eris, they found something remarkable. The surface of Eris appears to be dominated by methane ice. Methane is a simple molecule composed of one carbon atom and 4 hydrogen atoms. On Earth, methane exists as a gas, but in the extreme cold of the outer solar system, methane freezes into a solid ice that can coat planetary surfaces. This methane ice gives Eris an incredibly bright and reflective appearance. In fact, Eris reflects nearly 96% of the sunlight that reaches its surface. That makes it one of the most reflective objects in the entire solar system, even brighter than fresh snow on Earth. Such a bright surface is surprising because cosmic radiation and tiny meteorite impacts usually darken surfaces over time. Many objects in the outer solar system appear reddish or grey because their surfaces have been altered by billions of years of radiation. But Eris appears unusually pristine. Astronomers believe this may be because Eris has a thin atmosphere that occasionally forms and then freezes again during different parts of its orbit. To understand how this might work, we need to look at the extreme path Eris follows around the Sun. Eris does not travel in a nearly circular orbit like most planets. Instead, its orbit is highly elongated. At its closest point to the Sun, Eris comes within about 38 astronomical units. At its farthest point, it travels nearly 100 astronomical units away. This enormous variation means the amount of sunlight reaching Eris changes significantly over time. When Eris moves closer to the Sun, some of the methane and nitrogen ice on its surface may begin to sublimate, turning directly from solid ice into gas without becoming liquid. This process can create a temporary atmosphere around the dwarf planet, but as Eris moves farther away again, temperatures drop even lower. The gases then freeze and fall back onto the surface as fresh frost, covering older material with a new bright layer of ice. This process could explain why Eris appears so reflective. Its surface may periodically renew itself with fresh methane frost, constantly resetting the effects of space weathering. Scientists believe Pluto experiences a similar cycle. Although Pluto's atmosphere is thicker and more complex, but Eris exists in an environment even colder and darker than Pluto's. At its average distance from the Sun, the temperature on Eris is estimated to be around -243 degrees Celsius. At those temperatures, even nitrogen, a gas that makes up most of Earth's atmosphere, freezes into solid ice. This extreme cold creates a landscape that would look completely alien compared to anything on Earth. If you were somehow able to stand on the surface of Eris, the sky would appear almost completely black. The Sun would look like a bright star rather than a glowing disk. Its light would be about 1,000 times dimmer than the sunlight we experience on Earth. Despite the darkness, the surface around you would still appear surprisingly bright. The reflective methane frost would scatter what little sunlight exists, creating a faint icy glow across the landscape. The terrain itself is still largely unknown. Because Eris is so distant, scientists cannot yet map its mountains, valleys, or craters. However, based on what we know about Pluto and other icy bodies, astronomers suspect that Eris may contain a mixture of frozen plains, ridges, and impact craters formed over billions of years. Some scientists also suspect that Eris might have a rocky interior beneath its icy surface. Many icy dwarf planets appear to contain a mixture of rock and ice. Early in their history, radioactive elements within their interiors could generate heat. This heat might melt internal ice and create a subsurface ocean beneath the outer crust. Whether Eris once had such an ocean remains uncertain, but scientists believe its interior could still contain a layered structure of rock and frozen water. One of the most valuable clues about Eris's interior came from the discovery of its moon, Dysnomia. As astronomers carefully tracked Dysnomia's orbit around Eris, they were able to calculate the dwarf planet's total mass with remarkable precision. The results revealed that Eris is about 1.66 times 10 to the 22nd kilograms in mass. That might sound like an enormous number, and it is, but compared to Earth, it is still tiny. Eris has only about 0.27% of Earth's mass. Yet, compared to other dwarf planets, Eris is quite substantial. It is slightly smaller in diameter than Pluto, measuring about 2,326 kilometers across. But because it is denser, it actually contains more total mass. This density suggests that Eris contains a higher proportion of rocky material than Pluto. Scientists estimate that Eris is composed of roughly 70% rock and 30% ice. This mixture likely formed during the early stages of the solar system, when icy and rocky material combined to create the outer planets and their surrounding debris. The presence of rock within Eris also raises an interesting possibility. During the early history of the solar system, collisions between large objects were extremely common. Many dwarf planets likely experienced massive impacts that reshaped their surfaces or even created their moons. Astronomers suspect that Dysnomia may have formed in exactly this way. A giant collision between Eris and another object could have blasted debris into orbit around the dwarf planet. Over time, this debris would gradually combine to form a small moon. Similar events are believed to have created Earth's moon and Pluto's large moon, Charon. But unlike Pluto and Charon, which are relatively close together, Dysnomia orbits much farther away from Eris. Its orbit takes about 16 days to complete. From the surface of Eris, Dysnomia would appear as a faint, icy moon, drifting slowly across the dark sky. Beyond Dysnomia, the Eris system remains largely unexplored. No spacecraft has ever traveled close enough to capture detailed images. The incredible distance involved makes such a mission extremely difficult. At its current distance, Eris lies more than 14 billion kilometers from the Sun. Reaching such a distant world with a spacecraft would require decades of travel using current technology. For comparison, the New Horizons mission that visited Pluto in 2015 traveled for 9.5 years to reach its destination, and Pluto is much closer to the Sun than Eris. A mission to Eris could take 20 to 30 years or more. Because of these challenges, Eris remains one of the least explored major objects in the solar system. Yet, despite the lack of direct exploration, the dwarf planet continues to hold enormous scientific importance. Its discovery forced astronomers to rethink the classification of planets. Its unusual orbit provides clues about the violent gravitational interactions that shaped the outer solar system, and its bright, icy surface offers insights into the chemistry and climate of extremely distant worlds. In many ways, Eris represents a bridge between the familiar planets and the vast population of icy objects beyond Neptune. It reminds us that the solar system does not end with the planets we learned about in school. Instead, it extends outward into a vast frontier filled with frozen worlds, many of which remain undiscovered. And somewhere among those distant objects, there may be even larger worlds waiting silently in the darkness, just as Eris once did before its discovery changed everything. For most of human history, the solar system seemed relatively simple. There were the rocky planets close to the Sun, the giant gas planets farther out, and beyond them, the mysterious darkness where Pluto quietly orbited as the ninth and final planet. Textbooks, classroom models, and diagrams all showed the same picture: 9 planets arranged neatly around the Sun. But the discovery of Eris revealed something far more complicated. It showed that the solar system does not end with Pluto. Instead, Pluto marks the beginning of a vast region filled with countless icy worlds that orbit far beyond Neptune. These objects are part of an enormous population that scientists are still trying to understand, and Eris is one of the most important clues we have about that distant frontier. To understand the role Eris plays in the outer solar system, astronomers began examining the larger structure of this region. The Kuiper Belt was already known to contain thousands of icy objects, but scientists suspected that this was only the beginning. Beyond the Kuiper Belt lies another, even more distant and mysterious region, known as the scattered disk. Unlike the Kuiper Belt, which forms a relatively flat disk around the Sun, the scattered disk contains objects that travel in highly stretched and tilted orbits. These bodies are thought to have been thrown outward by gravitational interactions with the giant planets billions of years ago. When the solar system was young, the orbits of the giant planets were not exactly where they are today. Jupiter, Saturn, Uranus, and Neptune likely migrated through the early disk of debris that surrounded the Sun. As these massive planets moved, their gravitational forces scattered countless smaller objects outward into distant space. Some of those objects were flung into extremely distant orbits that extend far beyond the Kuiper Belt. Eris appears to be one of these scattered objects. Its orbit is both elongated and steeply tilted, suggesting that it experienced powerful gravitational interactions during the early history of the solar system. These interactions may have pushed it into its current orbit billions of years ago. But Eris is not the only object with such an unusual path. Astronomers have discovered several other distant worlds that belong to this scattered population. Some of them follow orbits that stretch hundreds of astronomical units from the Sun. One famous example is Sedna, an object whose orbit carries it more than 900 astronomical units away at its farthest point. These discoveries hint that the outer solar system is far more complex than scientists once imagined. Instead of ending neatly with Neptune or Pluto, the solar system gradually fades into a distant region filled with icy remnants from its formation. And within this distant population, Eris stands out as one of the largest known members. But understanding how objects like Eris formed requires looking back to the earliest moments of the solar system. About 4.6 billion years ago, our solar system began as a vast cloud of gas and dust, known as a solar nebula. This cloud slowly collapsed under its own gravity, forming a rotating disk around the young sun. Within this disk, particles of dust and ice began sticking together through collisions. Over time, these particles grew into larger bodies called planetesimals, the building blocks of planets. In the inner solar system, where temperatures were warmer, rocky materials dominated. These planetesimals eventually formed Mercury, Venus, Earth, and Mars. Farther from the Sun, temperatures were colder, ice became abundant, allowing planetesimals to grow larger more quickly. These icy building blocks eventually formed the cores of the giant planets. But not all of the material in the outer solar system became planets. Much of it remained scattered throughout the disk as smaller icy objects. These objects formed the populations we now call the Kuiper Belt and the scattered disk. Eris likely formed within this ancient disk of icy debris. Over time, gravitational interactions with the migrating giant planets may have thrown it into its current orbit far from the Sun. The result is a dwarf planet that spends most of its time in the extremely distant regions of the solar system. In fact, Eris is currently located near the farthest part of its orbit. Right now, it lies about 96 astronomical units from the Sun, making it one of the most distant known large objects in the solar system. At this distance, sunlight is incredibly faint. If you were standing on Eris today, the Sun would appear as an intensely bright star rather than a glowing disk. Daylight would be dim, casting long shadows across the icy surface. The darkness of this environment raises an interesting question. How do astronomers even detect objects so far away? The answer lies in careful observation of tiny movements against the background stars. Objects in the outer solar system move extremely slowly across the sky because they are so far from the Sun. By taking repeated images of the same region of the sky over several nights, astronomers can detect faint objects that shift slightly from one position to another. These movements reveal the presence of distant bodies orbiting the Sun. This method has allowed astronomers to discover thousands of Kuiper Belt objects and scattered disk objects over the past few decades. But detecting them is only the first step. Once an object is found, scientists must carefully track its motion for months or even years to determine its orbit accurately. This process is how astronomers eventually calculated the orbit of Eris and confirmed that it was one of the largest objects beyond Neptune. Yet, even with this knowledge, Eris remains incredibly difficult to study because it is so distant. Even the Hubble Space Telescope can barely resolve its disk. Most observations rely on measuring brightness changes rather than capturing detailed images. One surprising discovery from these brightness measurements is that Eris appears to rotate very slowly. Many small bodies in the solar system spin relatively quickly, completing a rotation in just a few hours. But Eris rotates once every 25.9 hours, giving it a day slightly longer than Earth's. This relatively slow rotation may be related to the presence of its moon, Dysnomia. Over long periods of time, gravitational interactions between a planet and its moon can alter the planet's rotation rate. Such tidal interactions are common throughout the solar system. Another interesting feature of Eris is its overall color. Unlike many objects in the Kuiper Belt that appear reddish or brown due to radiation damage, Eris looks neutral, or slightly bluish-white. This again supports the idea that its surface may be covered in fresh methane frost. But this bright surface also raises a deeper question. What processes keep renewing the ice on Eris? Some scientists believe the answer lies in seasonal cycles caused by its long orbit. As Eris moves closer to the Sun during its 557-year orbit, the increased sunlight may cause methane ice to sublimate into gas. This gas could form a temporary atmosphere around the dwarf planet. Later, as Eris moves farther away again, the atmosphere would freeze and fall back to the surface as fresh frost. Over hundreds of years, this process could slowly resurface the dwarf planet with new layers of ice. Although this idea is still theoretical, it provides a fascinating glimpse into the dynamic processes that may occur even in the most distant regions of the solar system. Despite its importance in reshaping planetary science, Eris remains largely unexplored. No spacecraft has ever visited it. No probe has ever photographed its landscape. Everything we know about this distant world comes from telescopes observing a tiny speck of light billions of kilometers away. But even from that immense distance, Eris has already played a profound role in expanding our understanding of the solar system. Its discovery revealed that Pluto was not unique. It showed that many large, icy worlds exist beyond Neptune, and it forced astronomers to rethink how planets are defined. Yet, Eris may only be one member of a much larger hidden population, because the outer solar system is still being explored, and somewhere in the distant darkness, even larger worlds may still be waiting to be discovered. Long before Eris was discovered, astronomers already suspected that the outer solar system might contain more objects beyond Pluto. But for decades, Pluto appeared to be alone. Telescopes simply were not powerful enough to reveal the faint, distant bodies orbiting far beyond Neptune. As technology improved, however, scientists began uncovering an entirely new population of icy worlds hidden in the darkness. The discovery of Eris was not just about finding a single distant object. It was part of a much larger story about the structure of our solar system and how it formed. To understand this story, we need to go back billions of years to the time when the solar system itself was still taking shape. In the early days of the solar system, the region beyond the giant planets was filled with enormous amounts of ice and rock. These materials were leftovers from the formation of Jupiter, Saturn, Uranus, and Neptune. While many of these materials combined to form large planetary bodies, much of the debris remains scattered throughout the outer disk. Over time, countless collisions between these icy fragments caused them to stick together and grow into larger objects. Some of these objects eventually reached sizes of hundreds or even thousands of kilometers across. These became the dwarf planets and large Kuiper Belt objects we observe today. However, the story did not stop there. During the early evolution of the solar system, the giant planets likely moved from their original positions. Computer simulations suggest that Jupiter, Saturn, Uranus, and Neptune migrated through the disk of debris that surrounded the young sun. This migration had dramatic consequences. As the giant planets moved, their immense gravity disturbed the orbits of countless smaller objects. Many of these icy bodies were thrown outward into distant regions of the solar system. Some were ejected completely into interstellar space. Others were scattered into elongated orbits that carried them far from the sun. This process created the scattered disk, the distant region where Eris now resides. The scattered disk is a chaotic environment compared to the relatively stable Kuiper Belt. Objects there follow stretched, tilted orbits that can carry them tens of billions of kilometers from the sun. These unusual trajectories reveal the violent gravitational interactions that occurred during the early history of the solar system. Eris appears to be one of the largest survivors of that chaotic period. Its orbit suggests that it may have formed closer to the sun before being pushed outward by the gravitational influence of Neptune. Over billions of years, it settled into the distant orbit we observe today. One of the most fascinating aspects of Eris is how long its journey around the Sun takes. A single year on Eris lasts about 557 Earth years. This means that since its discovery in 2005, Eris has barely moved along its orbit relative to the Sun. In fact, humanity has only observed a tiny fraction of its path around our star. Because its orbit is so large, Eris spends most of its time extremely far from the Sun, where temperatures are unimaginably cold. At these distances, sunlight is incredibly weak. The energy reaching Eris is less than 1,000th of what Earth receives. This environment creates some of the coldest conditions anywhere in the solar system. Yet, despite the darkness and cold, Eris remains one of the brightest objects known in the outer solar system. This brightness is caused by the reflective methane frost covering its surface. Methane ice reflects sunlight extremely efficiently, creating a dazzling white appearance even under dim illumination. But methane is not the only substance found on Eris. Observations suggest that the dwarf planet may also contain frozen nitrogen and possibly small amounts of carbon monoxide ice. These materials are similar to those found on Pluto, indicating that both worlds likely formed from similar ingredients during the early stages of the solar system. However, Eris is slightly denser than Pluto, which suggests that it may contain a larger proportion of rock beneath its icy exterior. Scientists believe that many dwarf planets formed through a process known as accretion. During accretion, smaller pieces of ice and rock gradually collided and stuck together, forming larger and larger bodies. Over time, gravity shaped these objects into spherical forms. Once an object becomes large enough for its own gravity to overcome the strength of its materials, it begins to pull itself into a rounded shape. This process is one of the key criteria used to classify dwarf planets. Eris easily meets this requirement. With a diameter of more than 2,300 kilometers, it is large enough for gravity to shape it into a nearly spherical world. Although its exact surface features remain unknown, scientists believe that Eris likely has a solid icy crust covering a deeper interior composed of rock and ice. Some researchers have even suggested that Eris may once have experienced internal heating early in its history. Radioactive elements within the dwarf planet's interior could have generated enough heat to partially melt internal ice, creating pockets of liquid water beneath the surface. If this occurred, it might have caused geological activity billions of years ago. Today, however, Eris appears to be a largely frozen and inactive world. Its great distance from the Sun prevents significant heating, and any internal heat that once existed has likely dissipated over billions of years. Yet, even a frozen world can reveal valuable clues about the past. Because Eris has remained so far from the Sun for most of its history, its surface may preserve ancient materials that date back to the earliest formation of the solar system. Studying such objects allows scientists to examine conditions that existed more than 4 billion years ago. In this sense, Eris acts like a time capsule from the distant past. It contains chemical and physical information that helps astronomers reconstruct the processes that shaped the planets. Another important aspect of Eris is its relationship with its moon, Dysnomia. Dysnomia is relatively small compared to Eris, but its presence provides essential data about the dwarf planet's mass and gravitational influence. By observing Dysnomia's orbit, astronomers can determine how strongly Eris pulls on nearby objects. This information revealed that Eris is actually more massive than Pluto, even though Pluto is slightly larger in diameter. That discovery surprised many scientists. For decades, Pluto had been the largest known object beyond Neptune. But Eris proved that Pluto was not unique. It was simply one member of a larger family of distant worlds. And this realization led to one of the most important conclusions in modern planetary science. The outer solar system contains far more large objects than anyone once imagined. Today, astronomers continue searching for additional dwarf planets and distant icy bodies. New surveys using powerful telescopes scan the sky for faint moving objects that may represent previously unknown worlds. Some scientists even suspect that a much larger object, sometimes called Planet 9, may exist far beyond the known planets. Although its existence has not yet been confirmed, evidence from unusual orbital patterns suggests that a massive unseen planet might be influencing distant objects in the outer solar system. If such a planet exists, it would orbit far beyond Eris. But regardless of whether Planet 9 is eventually discovered, the discovery of Eris already changed our understanding of the solar system forever. Before Eris was found, many people believed the solar system ended neatly with Pluto. Now we know that Pluto and Eris are only the beginning. Beyond them lies an enormous population of icy worlds stretching across vast distances from the Sun. These objects represent the leftover building blocks of planetary formation. They remind us that the solar system is far larger and more complex than the simple diagrams we once drew in textbooks. And among all these distant bodies, Eris remains one of the most important discoveries ever made in the outer solar system, because it forced humanity to reconsider one of the most basic questions in astronomy: what truly defines a planet? Even after the debate over Pluto's status settled and the term dwarf planet entered scientific vocabulary, Eris continued to raise new questions about the nature of the outer solar system. Its discovery did not simply change the definition of a planet, it also revealed that the distant regions beyond Neptune are far more populated, complex, and dynamic than astronomers had ever imagined. Before the late 20th century, scientists believed the solar system contained only a handful of major bodies beyond Neptune. Pluto appeared to be an isolated world drifting in the darkness, separated from the rest of the planets by an enormous empty gap. But Eris helped reveal that this assumption was completely wrong. Instead of a single distant planet, the outer solar system contains an enormous population of icy objects that formed during the earlier stages of planetary evolution. Many of these objects are relatively small, measuring only a few kilometers across. Others, like Pluto and Eris, are large enough for their own gravity to shape them into spherical worlds. This population is now known to include thousands of objects, and scientists believe there may be hundreds of thousands more still waiting to be discovered. These objects belong to several different regions beyond Neptune, each with its own unique characteristics. The closest region is the Kuiper Belt, a vast ring of icy debris that extends from about 30 to 50 astronomical units from the Sun. This region contains countless objects composed of frozen water, methane, nitrogen, and rock. Pluto itself is considered one of the largest Kuiper Belt objects. Beyond the Kuiper Belt lies the scattered disk, the region where Eris resides. Objects in the scattered disk follow extremely stretched and tilted orbits, suggesting that they were gravitationally disturbed by Neptune long ago. Many of these objects travel enormous distances during their orbits, sometimes venturing far beyond the Kuiper Belt before returning closer to the Sun again. Eris is one of the most massive known members of this scattered population, but the scattered disk itself may only be part of an even larger structure. Far beyond the scattered disk lies a hypothetical region called the Oort cloud. This enormous spherical shell of icy objects may extend tens of thousands of astronomical units from the Sun. If it exists as predicted, it would represent the outermost boundary of the Sun's gravitational influence. The Oort cloud is believed to be the source of long-period comets that occasionally enter the inner solar system. While Eris does not orbit within the Oort cloud, its distant path hints at the complex gravitational interactions that shaped these outer regions billions of years ago. Understanding these distant regions helps astronomers reconstruct the early history of the solar system. During the first few 100 million years after the Sun formed, the young planetary system was a chaotic environment filled with collisions and gravitational disturbances. The giant planets migrated through the disk of debris surrounding the Sun, scattering icy bodies in all directions. Many of these objects were thrown into distant orbits like the one followed by Eris, Others were completely ejected from the solar system and now drift through interstellar space. Computer simulations of this period suggest that the outer solar system originally contained far more material than it does today. Over time, gravitational interactions removed much of that material, leaving behind the scattered populations we observe now. Eris represents one of the survivors of that turbulent era. Its orbit preserves a record of the powerful forces that once reshaped the solar system. But Eris also raises another fascinating question. If the outer solar system contains so many objects, could there be worlds even larger than Eris still waiting to be discovered? Some astronomers believe the answer may be yes. Over the past decade, scientists have noticed unusual patterns in the orbits of several extremely distant objects beyond Neptune. These objects appear to cluster in similar directions, as if they are being influenced by the gravity of something massive. One possible explanation is the existence of a distant, undiscovered planet, often referred to as Planet 9. According to some models, Planet 9 could be several times more massive than Earth and orbit the Sun at distances hundreds of times farther than Earth's orbit. Such a planet would be extremely faint and difficult to detect, which is why it may have escaped discovery so far. If Planet 9 does exist, it could help explain the unusual orbital patterns seen among scattered disk objects. However, the evidence for Planet 9 is still indirect, and astronomers continue searching the sky for confirmation whether Planet 9 exists or not. The discovery of Eris already demonstrated that large objects can exist far beyond the known planets. And this realization transformed how astronomers approach the search for distant worlds. Modern telescopes now conduct large sky surveys designed specifically to detect faint objects moving slowly across the sky. These surveys use sensitive digital cameras capable of capturing enormous areas of space in a single image. By comparing images taken on different nights, astronomers can identify distant objects that shift slightly relative to background stars. This technique has led to the discovery of thousands of new Kuiper Belt objects and scattered disk bodies over the past 2 decades. Some of these objects are only a few hundred kilometers across, while others approach the size of dwarf planets. Among the most notable discoveries are Haumea and Methane, 2 large icy worlds that were also classified as dwarf planets shortly after Eris was discovered. Haumea is particularly unusual because of its elongated shape and extremely rapid rotation. Methane, on the other hand, appears to have a bright icy surface somewhat similar to Pluto and Eris. Together, these objects form a small group of large dwarf planets that dominate the outer solar system beyond Neptune. But even these worlds may represent only a small fraction of what exists out there. Astronomers believe the outer solar system could contain dozens of dwarf planets and possibly many more large objects that have yet to be detected. Finding them is extremely challenging because of the vast distances involved. Light from these objects is incredibly faint, and their slow motion across the sky makes them difficult to distinguish from distant stars. Nevertheless, the search continues. Each new discovery adds another piece to the puzzle of how our solar system formed and evolved. Eris remains one of the most important members of this distant population. Its discovery marked a turning point in planetary science. It forced astronomers to reconsider the classification of planets and revealed that the outer solar system contains far more large objects than previously thought. But despite its importance, Eris itself remains largely unexplored. No spacecraft has ever traveled there. No detailed images of its surface exist. Everything scientists know about Eris comes from faint measurements of reflected sunlight captured by telescopes here on Earth. One day, however, this may change. Some researchers have proposed sending a spacecraft mission to explore the distant dwarf planets beyond Neptune. Such a mission could reveal details about their geology, composition, and internal structure. A spacecraft visiting Eris would likely take several decades to reach its destination, but the scientific rewards could be enormous. By studying Eris up close, scientists could learn more about the building blocks that formed the outer solar system. They could examine the chemistry of its icy surface and search for clues about its internal structure. They might even discover unexpected geological features shaped by processes we have not yet imagined. Until that day comes, Eris will remain a distant and mysterious world. But even from billions of kilometers away, it has already changed the way we understand our cosmic neighborhood, because Eris revealed something profound. The solar system is not a small collection of planets orbiting neatly around the sun. It is a vast and complex system filled with countless hidden worlds stretching far into the darkness of space. The debate that followed the discovery of Eris was immediate and intense. For decades, the structure of the solar system had seemed relatively stable. There were 9 planets, each with a clearly defined place in textbooks, diagrams, and educational models. Pluto, though small and distant, still held its position as the 9th planet orbiting beyond Neptune. But the discovery of Eris disrupted that familiar picture. Suddenly, astronomers were faced with an uncomfortable possibility. Pluto might not be unique. If another object of similar size existed beyond Neptune, then perhaps Pluto was simply one member of a much larger population of icy worlds. This realization forced scientists to confront a question that had never been clearly answered before. What exactly is a planet? For centuries, the word planet had evolved through historical usage rather than strict scientific definition. In ancient times, the term referred to wandering stars that moved across the sky relative to the background constellations. Mercury, Venus, Mars, Jupiter, and Saturn were known as planets because they moved differently from ordinary stars. Later discoveries expanded that list. Uranus was discovered in 1781, Neptune in 1846, and Pluto in 1930. Each new discovery simply added another planet to the solar system without requiring a formal definition. But the discovery of Eris made that approach impossible to maintain. If Eris was roughly the same size as Pluto, and possibly even more massive, then it seemed reasonable to call it a planet as well. However, doing so would raise an even larger problem. Astronomers were already discovering many other large objects in the Kuiper Belt. Some of these objects were approaching Pluto's size, others were only slightly smaller. If all of them were classified as planets, the number of planets in the solar system could quickly grow to dozens. Some scientists estimated that there might be hundreds of large objects in the outer solar system capable of qualifying as planets under the old definition. For many astronomers, this outcome seemed impractical. The concept of a planet had always implied a relatively small group of dominant worlds. Expanding the list indefinitely would blur the distinction between planets and the countless smaller bodies orbiting the Sun. This growing debate led the International Astronomical Union, IAU, to organize a formal discussion about the definition of a planet. In 2006, astronomers from around the world gathered in Prague for the IAU General Assembly. One of the central topics of the meeting was the classification of Pluto and the newly discovered Eris. Scientists presented several proposals for defining a planet. One suggestion was that any object large enough to become spherical due to its own gravity should be considered a planet. Under this definition, Pluto and Eris would both qualify, along with several other large objects. But this approach would also dramatically increase the number of planets in the solar system. Another proposal introduced an additional requirement. A planet must dominate its orbital region gravitationally. This means the object must have cleared most other debris from its path around the Sun over billions of years. In other words, a planet should be the largest and most influential body in its orbital neighborhood. Under this stricter definition, the 8 major planets easily qualified, Mercury, Venus, Earth, and Mars, dominate their regions of the inner solar system. The giant planets, Jupiter, Saturn, Uranus, and Neptune, control even larger gravitational zones. Pluto, however, did not meet this requirement. Pluto shares its orbital region with countless other objects in the Kuiper Belt. It does not dominate that region gravitationally, and neither does Eris. After days of debate, the IAU voted to adopt a new definition. According to the final resolution, a planet must satisfy 3 criteria. First, it must orbit the Sun. Second, it must have enough mass for gravity to pull it into a roughly spherical shape. Third, it must have cleared the neighborhood around its orbit. Pluto and Eris satisfied the first 2 conditions, but they failed the third. As a result, they were placed into a new category called dwarf planets. This decision officially reduced the number of recognized planets in the solar system from 9 to 8. The announcement immediately sparked controversy around the world. Many people had grown up learning that Pluto was the 9th planet. Generations of students had memorized its place in the solar system. For them, Pluto's reclassification felt almost like losing a familiar member of the planetary family. Some scientists also criticized the decision. A number of astronomers argued that the clearing the neighborhood criterion was too vague or unfair to distant objects like Pluto and Eris. Others pointed out that even Earth shares its orbit with thousands of small asteroids known as near-Earth objects. Despite these objections, the new definition remained in place. Pluto and Eris were now officially classified as dwarf planets. But in a curious way, Eris had accomplished something remarkable. Without ever being visited by a spacecraft, and without even being visible to the naked eye, this distant world had forced humanity to rethink one of the most basic concepts in astronomy. The discovery of Eris had triggered the redefinition of the solar system itself. And yet, despite its importance, Eris remained an incredibly distant and mysterious object. At the time of its discovery, Eris was located nearly 96 astronomical units from the Sun. That distance is so great that sunlight takes more than 13 hours to reach it. From Earth, Eris appears only as a faint point of light, moving slowly against the background stars. Even the largest telescopes cannot easily resolve its surface. Because of this, most of what we know about Eris comes from indirect measurements. Astronomers analyze the brightness of the object to estimate its size. They study the spectrum of its reflected light to determine its chemical composition, and they observe the orbit of its moon Dysnomia to calculate its mass. These techniques allow scientists to build a surprisingly detailed picture of a world that lies billions of kilometers away. Yet many mysteries remain. For example, the exact appearance of Eris's surface is still unknown. Scientists believe it is covered in bright methane frost, but the details of its landscape, mountains, valleys, or impact craters remain hidden from view. Another unanswered question involves the internal structure of the dwarf planet. Although Eris is primarily composed of rock and ice, it is unclear whether its interior contains layers similar to those found inside Pluto. Some models suggest the possibility of a dense, rocky core surrounded by a mantle of frozen water. Others propose that the dwarf planet may have experienced internal heating early in its history, possibly creating pockets of liquid water beneath the surface. Without direct exploration, however, these ideas remain speculative. The extreme distance of Eris makes sending a spacecraft there extremely challenging. A mission to Eris would require decades of travel using current propulsion technology. Even the fastest spacecraft launched from Earth would need 20 to 30 years to reach such a distant destination. Despite these challenges, some scientists have begun considering future missions to explore the distant dwarf planet. Such missions could provide unprecedented insights into the chemistry, geology, and history of the outer solar system. For now, however, Eris remains a remote frontier, a frozen world, drifting slowly through the darkness far beyond Neptune. Yet its impact on science has already been profound, because Eris forced astronomers to reconsider the structure of our solar system. It revealed that Pluto was not unique, and it showed that the distant regions beyond Neptune contained far more large worlds than anyone once imagined. In a way, Eris did exactly what its name suggests. In Greek mythology, Eris was the goddess of discord, known for provoking conflict among gods and mortals alike, and fittingly, The discovery of this distant world sparked one of the most heated debates in modern astronomy, but from that debate emerged a deeper understanding of our cosmic neighborhood. The solar system is not a simple collection of planets orbiting the Sun. It is a vast and complex system filled with hidden worlds waiting to be discovered. Even though Eris is one of the most important discoveries in modern planetary science, it remains one of the least explored worlds in the solar system. Unlike Pluto, which was visited by the New Horizons spacecraft in 2015, Eris has never been observed up close by any spacecraft. Everything scientists know about this distant dwarf planet has been gathered from telescopes observing a faint point of light billions of kilometers away. This distance is the primary reason Eris remains so mysterious. At its current position in its orbit, Eris lies nearly 14 billion kilometers from the Sun. From Earth, that distance is so vast that even powerful telescopes struggle to resolve details about the dwarf planet. To most instruments, Eris appears as nothing more than a tiny bright dot moving slowly across the sky. Yet, despite this limitation, astronomers have managed to learn a surprising amount about this world. One of the key techniques used to study distant objects like Eris is called spectroscopy. This method analyzes the light reflected from an object and breaks it into its component wavelengths. Each chemical substance reflects and absorbs light in a unique way, creating identifiable patterns within the spectrum. By examining these patterns, scientists can determine which materials are present on a distant surface. When astronomers analyzed the light coming from Eris, they found clear evidence of methane ice covering much of its surface. Methane is the same compound found on Pluto and several other icy bodies in the outer solar system. Under extremely cold conditions, methane forms a bright, reflective frost that covers the surface. This methane ice explains why Eris appears unusually bright, despite being so far from the Sun. In fact, Eris reflects nearly 96% of the sunlight that reaches it. That level of reflectivity makes it one of the most reflective objects in the entire solar system. For comparison, Earth reflects only about 30% of incoming sunlight. Scientists believe this high reflectivity may be caused by seasonal cycles on Eris. Because Eris follows an extremely elongated orbit around the Sun, the amount of sunlight reaching the dwarf planet changes dramatically over time. When Eris moves closer to the Sun, some of the methane ice on its surface may begin to sublimate, turning directly from solid into gas. This gas could temporarily form a thin atmosphere surrounding the dwarf planet. But as Eris travels farther away again, the temperature drops even lower. The methane gas would then freeze and fall back onto the surface as fresh frost. This process could effectively resurface Eris over time, covering older areas with new layers of bright ice. While this idea is still theoretical, it offers a possible explanation for why Eris appears so unusually reflective. Another important discovery about Eris involves its density. By observing the orbit of its moon, Dysnomia, astronomers were able to calculate the mass of Eris with remarkable precision. Combining this mass measurement with estimates of its size allowed scientists to determine the dwarf planet's density. Eris turned out to be surprisingly dense for an icy object. Its average density is about 2.5 grams per cubic centimeter, which suggests that it contains a significant amount of rocky material beneath its icy surface. This density indicates that Eris may be composed of roughly 70% rock and 30% ice. This composition is similar to that of Pluto and several other large Kuiper Belt objects. However, the internal structure of Eris remains largely unknown. Many scientists believe that dwarf planets, like Eris, may have layered interiors. A dense rocky core could lie at the center, surrounded by a mantle of water, ice, and other frozen materials. In some cases, internal heat generated by radioactive elements may have melted portions of the interior long ago. This process could have created temporary subsurface oceans beneath the icy crust. Whether Eris ever contained such an ocean is still uncertain, because Eris formed far from the Sun and experienced extremely low temperatures throughout its history. Any internal heating would have been limited. However, the presence of radioactive elements within its rocky core could have generated enough heat to melt ice during the early stages of its formation. If such melting occurred, it might have allowed water and other volatile substances to move within the dwarf planet's interior. Over time, however, Eris would have cooled significantly. Today, it is believed to be a largely frozen world with little or no internal geological activity. But even a frozen world can preserve valuable clues about the early solar system. The surface of Eris has likely remained relatively unchanged for billions of years. Because it lies so far from the Sun, the rate of impacts from comets and asteroids is lower than in the inner solar system. This means that much of the surface may still preserve ancient features formed shortly after the dwarf planet itself formed. Unfortunately, these features cannot yet be observed directly. Current telescopes simply cannot resolve such details at the enormous distance separating Earth from Eris. Future technological advances may eventually allow astronomers to study distant dwarf planets in greater detail. Next-generation telescopes, such as the Extremely Large Telescope and other powerful instruments currently under construction, may provide sharper observations of distant objects like Eris. These telescopes will have mirrors far larger than any existing observatory, allowing them to collect more light and detect fainter objects. With these capabilities, scientists hope to measure the surface properties of distant dwarf planets with greater accuracy. They may even be able to detect subtle variations in brightness across the surface of Eris, hinting at differences in terrain or composition. But the ultimate goal for many planetary scientists is far more ambitious. They want to send a spacecraft to the distant dwarf planets themselves. Exploring Eris directly would provide invaluable information about its geology, atmosphere, and internal structure. However, the distance involved makes such a mission extremely challenging. Even the fastest spacecraft ever launched from Earth would require decades to reach Eris. The New Horizons mission that visited Pluto traveled at enormous speeds and still took nearly 10 years to reach its destination. Because Eris is currently much farther from the Sun than Pluto, a mission there would likely require 25 to 30 years of travel. Despite these challenges, scientists continue studying potential mission concepts. One possibility is a spacecraft similar to New Horizons that would fly past Eris at high speed, capturing detailed images and scientific data during a brief encounter. Another idea involves advanced propulsion systems that could allow a spacecraft to slow down and enter orbit around the dwarf planet. Such a mission would provide an unprecedented opportunity to study one of the most distant worlds known in our solar system. For now, however, Eris remains far beyond the reach of our spacecraft. It drifts silently through the outer darkness, orbiting the Sun once every 5.5 centuries. Yet, even from this immense distance, its discovery transformed astronomy, because Eris revealed something remarkable. The solar system does not end with the 8 major planets. Instead, it extends outward into a vast frontier filled with icy worlds, many of which remain undiscovered. Eris is one of the first of these distant giants to be found, but it will almost certainly not be the last. For a long time, Pluto marked what many people believed was the outer boundary of the solar system. Beyond its orbit stretched an almost unimaginable darkness, a region where sunlight was weak and temperatures were colder than nearly anywhere else known. For decades, astronomers assumed that very little existed out there, except for occasional comets drifting inward from the distant reaches of space. But the discovery of Eris helped reveal that this assumption was far from correct. Instead of an empty void, the outer solar system appears to contain a vast population of icy worlds. Many of these objects are remnants from the earliest days of planetary formation, preserved in the cold environment beyond Neptune. They represent pieces of a cosmic puzzle that scientists are still trying to assemble. Eris became one of the most important clues in that puzzle. Its discovery confirmed that Pluto was not unique. There were other objects nearly the same size orbiting the Sun far beyond Neptune. This realization forced astronomers to rethink the structure of our planetary system, but Eris also raised a deeper question. If Eris exists, how many other large worlds might still be hidden in the darkness? Over the past 2 decades, astronomers have continued scanning the skies in search of distant objects. Large survey telescopes repeatedly photograph wide areas of the sky, looking for tiny points of light that slowly shift position from night to night. This slow motion is a signature of distant objects orbiting the Sun. Through these surveys, scientists have discovered thousands of Kuiper Belt objects and scattered disk objects. Some are only a few kilometers across, while others measure hundreds of kilometers in diameter. A handful are large enough to qualify as dwarf planets. Among these are Haumea, Makemake, Sedna, and several other candidates that may eventually be officially classified as dwarf planets as well. Each new discovery adds to the growing picture of the outer solar system as a vast and diverse region filled with icy bodies. But even with all these discoveries, Eris still stands out. One reason is its extreme orbit. Unlike Pluto, which follows a moderately tilted orbit, Eris travels along a path that is both highly elliptical and steeply inclined relative to the plane of the solar system. Its orbital tilt is about 44 degrees, meaning that it moves far above and below the flat disk in which most planets orbit. This unusual orbit suggests that Eris experienced strong gravitational disturbances in the distant past. One possibility is that Eris formed closer to the Sun before being pushed outward by Neptune during the early migration of the giant planet. Another possibility is that interactions with other large objects in the early solar system altered its path over time. Computer simulations of the early solar system suggest that such gravitational interactions were common during the first few 100 million years after the Sun formed. The giant planets may have migrated through the disk of debris that surrounded the young solar system. As they moved, they scattered countless smaller objects into distant orbits. Some objects were flung outward into the scattered disk, others may have been ejected completely from the solar system. Eris appears to be one of the survivors of this chaotic era. Its orbit carries it from about 38 astronomical units at its closest point to nearly 100 astronomical units at its farthest distance from the Sun. This enormous path takes more than 5.5 centuries to complete. Because Eris moves so slowly along its orbit, astronomers have observed only a tiny portion of its journey around the Sun. Right now, Eris is located near the farthest part of its orbit, where temperatures are at their lowest and sunlight is extremely weak. At this distance, the Sun would appear as a bright star rather than a large glowing disk. Despite these conditions, Eris remains visible to telescopes because of its reflective surface. The methane ice covering the dwarf planet reflects sunlight extremely efficiently, allowing astronomers to detect it even from billions of kilometers away. But the extreme distance also means that Eris is unlikely to be visited by a spacecraft anytime soon. Exploring such distant worlds presents enormous technical challenges. The farther a spacecraft travels from the Sun, the less solar energy is available to power its systems. Missions to the outer solar system often rely on nuclear power sources to generate electricity for instruments and communications. Even with powerful propulsion systems, reaching the outer regions of the solar system requires many years of travel. For example, the New Horizons spacecraft, which flew past Pluto in 2015, traveled for nearly 10 years before reaching its destination. Eris is currently much farther away than Pluto was at the time of the New Horizons encounter. A mission to Eris would likely require 20 to 30 years or more of travel time. Because of these difficulties, Scientists currently rely on telescopes rather than spacecraft to study Eris. Fortunately, modern telescopes have become incredibly powerful. The Hubble Space Telescope has been used to measure the size of Eris and confirm the presence of its moon, Dysnomia. Ground-based observatories equipped with adaptive optics systems have also provided important data about its brightness and rotation. Future telescopes may reveal even more details. The James Webb Space Telescope and upcoming extremely large ground-based observatories may allow astronomers to study the chemical composition of Eris with greater precision. These instruments could detect subtle variations in the dwarf planet's surface materials and provide new insights into its geology. Yet, even with these advanced technologies, many mysteries about Eris remain. For example, scientists still do not know exactly how its surface evolved over billions of years. Did Eris experience geological activity early in its history? Did internal heating create temporary oceans beneath its icy crust? Or has it remained largely frozen and inactive since the time it formed? These questions remain unanswered, but one thing is certain. The discovery of Eris fundamentally changed how scientists think about the outer solar system. It revealed that Pluto was only one member of a much larger population of distant worlds. It showed that the solar system is far more extensive than we once believed, and it reminded astronomers that even in regions we thought we understood, entirely new discoveries can still reshape our understanding of the cosmos. Eris may be far away and difficult to study, but its impact on planetary science has been enormous. It forced humanity to redefine what a planet is, and it opened the door to the exploration of an entire new frontier beyond Neptune. A frontier that may still contain countless hidden worlds waiting to be discovered in the darkness, far beyond the familiar planets of the inner solar system, beyond the giant worlds of Jupiter and Saturn, and even beyond the icy orbit of Pluto. Eris continues its slow and silent journey through the darkness of space. It moves along a vast orbit that takes more than 5 centuries to complete, circling the Sun at distances so extreme that sunlight becomes little more than a faint glow against the frozen surface. From Earth, Eris appears as nothing more than a tiny point of light, drifting slowly among distant stars. Yet, despite its faint appearance, this distant dwarf planet has had a profound influence on our understanding of the solar system. Before Eris was discovered, many people believed that the solar system ended with Pluto. The structure of our planetary system seemed relatively simple. 9 planets orbiting the Sun in an orderly arrangement. Pluto occupied the outermost position, marking what appeared to be the edge of the planetary family. But the discovery of Eris revealed that this picture was incomplete. Instead of a single distant planet, astronomers discovered that the region beyond Neptune contains a vast population of icy worlds. These objects are remnants from the early formation of the solar system, preserved in the cold darkness far from the Sun. Eris became one of the most important examples of these distant bodies. Its size, mass, and unusual orbit showed that Pluto was not unique. Other worlds of comparable scale existed in the outer solar system, hidden from view for most of human history. This realization forced scientists to reconsider how planets should be defined. For decades, the word planet had been used without a strict scientific definition. The discovery of Eris made it clear that a new classification system was needed to distinguish between the dominant planets and the numerous smaller bodies beyond Neptune. As a result, the category of dwarf planets was created. Pluto and Eris became the most famous members of this new class of objects. Along with other dwarf planets like Haumea and Makemake, they represent a transitional group between the major planets and the countless smaller bodies scattered throughout the outer solar system. Although some people were disappointed by Pluto's reclassification, the discovery of Eris ultimately expanded our understanding of the solar system, rather than diminishing it. Instead of a small collection of 9 planets, We now know that the solar system contains an enormous variety of worlds: rocky planets, gas giants, icy moons, dwarf planets, comets, and countless smaller bodies, all orbiting the Sun in complex and dynamic patterns. The discovery of Eris also highlighted how little we still know about the distant regions of our cosmic neighborhood. Even today, astronomers continue searching the skies for new objects beyond Neptune. Large sky surveys scan the heavens for faint points of light that slowly shift against the background stars. Each new discovery adds another piece to the puzzle of how the solar system formed and evolved. Some scientists believe that many more dwarf planets may exist in the outer solar system, perhaps dozens or even hundreds. Others suspect that a much larger object, sometimes called Planet 9, may still be waiting to be discovered far beyond the known planets. Although evidence for such a planet remains uncertain, unusual patterns in the orbits of distant objects suggest that something massive could be influencing them. If such a world exists, it would orbit far beyond Eris, perhaps hundreds of astronomical units from the Sun. But even without the discovery of additional planets, Eris has already played a crucial role in shaping modern astronomy. It demonstrated that our solar system is far more complex than once believed. It revealed that large objects can exist at enormous distances from the Sun, and it reminded scientists that the exploration of our cosmic neighborhood is far from complete. Eris itself remains a mysterious world. No spacecraft has ever visited it. No probe has ever photographed its surface in detail. Everything we know about this distant dwarf planet comes from telescopes observing its faint light across billions of kilometers of space. Yet, even from this distance, astronomers have learned that Eris is covered in reflective methane ice, that it possesses a small moon called Dysnomia, and that it follows an orbit tilted dramatically relative to the rest of the solar system. These clues offer glimpses into the processes that shaped the outer solar system billions of years ago. One day, future missions may travel to these distant dwarf planets, just as New Horizons transformed our understanding of Pluto. A spacecraft exploring Eris could reveal landscapes unlike anything we have seen before. It might discover mountains of frozen methane, ancient impact craters preserved for billions of years, or unexpected geological features hidden beneath layers of ice. Until that day arrives, Eris will remain a distant frontier, a frozen world drifting through the outer darkness of our solar system. But its discovery has already changed how we see our place in the cosmos, because Eris taught us something profound. The solar system does not end with the planets we learned about in school. It extends far beyond them, into a vast region filled with hidden worlds, ancient debris, and mysteries still waiting to be explored. And somewhere in that distant darkness, other discoveries may still be waiting, just as Eris once was before its discovery reshaped the solar system forever.